That was Mark.
That was
All
Mark.
right.
That was Mark.
All right. Okay. So last week, Friday, we were getting into talking about how carburetors work. And what we had started with was we have to have some way for the engine to measure the air coming through. And what we did is we said we were going to use a Venturi. Now, be mindful that almost all aircraft carburetors are updraft carburetors, which means they go on the bottom of the engine and they suck air from the bottom and it goes up into the engine, as opposed to an automobile, which you would not want to do that because the carburetor then would be near the ground where all the dirt is, and they go from the top down into the engine. So aircraft, for the most part, go from the bottom up. So we created this Venturi over here. Venturi. There we go. And so what is the Venturi and what is it all about? Well, Venturi does a couple of things, or it does. So it allows us to measure the air coming in. So one, it creates the low pressure needed to draw fuel from the discharge nozzle. So it creates the low pressure needed to draw fuel from the discharge nozzle. Fuel from the discharge nozzle. Discharge nozzle. Well, how does it work? Well, it operates on Bernoulli's principle. B-E-R-N-O-U-L-L-I, Bernoulli's. Got to get rid of that now. Not gonna, because on a different layer. Bernoulli's principle. Bernoulli's principle. And I'm sure that Phil covered this quite a bit, but what Bernoulli's principle says, as far as air goes, as the velocity, of the air going through it increases, then the pressure will decrease. Pressure will decrease. All right, and then the second point here, what's my second point? So as the velocity increases, the pressure will decrease. Well, that's kind of cool because the more the velocity increases, the more the pressure will decrease or create a vacuum, if you want to think of it that way. So it's a great way to measure something. It doesn't stay just constant. So the more air that flows, the more air that flows, the greater the suction, the greater the suction, the greater the suction, and the more fuel, and the more fuel is drawn out of the discharge nozzle. Let me think here. A nice white space to write on would be nice. Let me see if I can do something here. Make a new slide here and then let's delete. All right, so Stephen, while I'm doing this and you're getting caught up with your notes, Stephen said, I have a question. If we don't talk on chat via voice, won't it factor to overall grade of our focus amount? It might affect you a little bit, but it's better. But it'll affect everybody equally, so it won't matter. What does B, the more airflow? B, the more air that flows, my pen got kind of messed up there. The more air that flows, that can be a comma. The more air that flows, that is, more air flows through the Venturi, the greater the suction in the Venturi, and the more fuel is drawn out the discharge nozzle. And I'm going to explain that actually as soon as I can. What I wanted was a nice white area to write on, so I was creating one over here on this side that I can draw on. I suppose I could have used Word too, huh? Let me see. Let's try Word. See what happens with that. All right, so you guys should be able to see my Word doc right here. If you can't, say so. Yep, I can draw. Can I change my colors? Maybe I should learn to do something on the fly. I don't know. Got it. Slideshow. Current slide. There we go. I'm sure you can see that. All right, and this will allow me to change some colors. All right, so what we started with yesterday, and I was making a drawing, is we started with a Venturi. No. There we go, pen. We'll go black. So we started with a Venturi, and I'll make it kind of over here. And we have to remember Venturi is actually a three-dimensional item that is, well, we were pretending like we were on a desert island. So if you will, it was some sort of a piece of bamboo, because bamboo is round and Venturi is actually symmetrical, and it's got to be closed off towards the middle. So when air goes through it, the air speeds up. Just like it's, if you kind of look at it, it's almost like having two wings. So this is like one wing right here, and the air is flowing. Well, if I do it nice, air is flowing through the wing and has to speed up as it go over the wing. That's what made the wing fly. My wing will work better that way, but it doesn't go that way. All right, so we had this, this Venturi, and we now, as we discussed, as the air flows through, the Venturi is going to create a suction. Well, that suction is going to be used to draw fuel out. So next to this, I had put a tank or reservoir of fuel. And this is really how it works in a carburetor. We have a reservoir here. And let's see if we can make blue. Oh, well, different blue. There we go, dark blue. And this has our fuel in it, because fuel is blue. And the fuel came to us from the fuel tank, which was up higher because we have a gravity feed system, and that's fine. And so we have it plumbed in here, and it goes up to a fuel tank, up to our fuel tank. And of course, then that has fuel in it. That has fuel always in there. And then we have to have, so because the fuel tank is up higher and the fuel is going to come in, if we just put a hole right here and the fuel came in, it would flow over and run all over the ground, and that wouldn't be very good. And so this particular, well, not this particular, all of them, they have a float that goes in here, and the float, just like toilet bowl technology, is on an arm. I wish it didn't do that, on an arm. And that arm has a fulcrum. A fulcrum is the point where, stop it, where it moves up and down. And then this would have some sort of needle that would go in there and stop the flow of fuel from coming in. So as the float went up, it'll push the needle down and lock that off. As the fuel goes down, then it will drop this down and let fuel come in. So it's going to keep our fuel, it's going to attempt to keep it at a very exact level, which, yes, thank you, J-Rod, the monkeys. The monkey did do the job there for a while, but the monkey union is pretty much put a stop to this sort of activity these days. And that's, you know, that's what unions are for. All right, so from this area, the fuel is going to come up and it's going to go through a fuel discharge nozzle. Now, the fuel discharge nozzle has to be a little bit taller than the fuel level because the fuel is going to come down here, and it is actually supposed to go in and stop at the exact same level, because that's what fuel does. It's going to seek its level. And so the discharge nozzle has to be just a little bit taller than that, so that the fuel doesn't just run out all over the ground when the engine isn't running. Now, interestingly enough, or maybe it's not interesting, maybe it's a really boring thing. There are really two different types of different makers of carburetors in general aviation. So Marvel Shebler is the old school name. Marvel Shebler became Facet, became Precision Aeromotive, but I'm just going to call it Marvel Shebler because I'm an old guy. And so Marvel Shebler is the more complicated, modern carburetor. But if you look at like a Cessna 140 or a Piper Cub or some of the really old planes made in the 40s, they all had Stromberg carburetors. And that's the first carburetor you guys will do in lab if we all live long enough to go to the lab. And so what the Stromberg, the old style carburetors, they actually have a problem, and they don't seal really well with this little needle area here. So what happens is the fuel tends to come up and wants to rise up a little bit further because it didn't seal right here, and the fuel tends to drip out nonstop. And so whenever you shut one of those engines off, you always have to shut off a fuel valve, which is located in the fuel line. So what happens if your fuel float here gets a little hole in it? Well, if it gets a little hole and it sinks down, or if it's not adjusted right and it sinks down a little bit, then this level is going to rise, and it is going to, first of all, spill over when the engine is not running. Now, when the engine is running, this level here, let me see, get something a little bit different color here. This level between right here and right here, right there, that is called something. Where's my notes here? So that is called the fuel metering force. And I'm going to talk about the fuel metering force. Well, since I brought it up, I'll talk about it right now. So that's the fuel metering force. So, all right, this is where we left off yesterday. Let me see, what do I want to do here? Yeah, I'm just going to jump around here. So Venturi, I want to go to fuel metering force since I talked about it. Get my other screen back up. Oh, why are you doing that? All right, so we are right here. So let me look at my group chat. Can we answer the stuck float? Yes, either flood the engine or have, no, you won't have fuel starvation. It would be the other way around. Well, if it got stuck in the up position, you would. So, all right, let's see, the more fuel. So what can I put here? And I'm gonna get away from my notes, and this could be dangerous for me. But I brought it up. So, oops, what did I want to talk about? Fuel metering force. Let's put this here. So, fuel metering force. I personally don't like this definition. I don't like what they call it. And it's really going to get confusing later on as we talk about other things. But this is what it is. It is the difference. Oops, I already screwed up. The difference. Now, I'm going to give you the difference in pressure from the float bowl to the Venturi. Also, we can further describe it as the force required to lift the fuel from its normal. Oops, it's not apostrophe F, that'd be it is. So it's possessive, it's normal level to the discharge point, All right, so back to my drawing. Where did my drawing go? All right, so back to our little drawing right here. All right, so far we've got this semi-working carburetor, and pen going here. Oh, we'll get this going. Okay, so what we've got then is the fuel comes in, we've got a float that's going to automatically adjust this level. We have this right here. Let me see. This dimension right here is very critical, and it ties into the fuel metering force, which one of the definitions was the force required to lift the fuel from its normal level to the discharge point. We'll talk more about that a little bit later, but we have to have it down here a little bit. Now, one of the things that well, if we were going to take this out, we were going to give it a shot, and we had kind of played around with that. So we stick somebody in the cockpit, and we have them start it up. Well, one of the first things we would find out is this thing will never start in this way, because as the engine is cranked over on the starter, there is not enough air coming through here to create a significant difference. There won't create a low pressure area enough to raise the fuel out of the discharge nozzle. So you can crank all day. Nothing's going to happen. So eventually you'll wear out your battery and it'll die. So let's see, Dominic, do you have a question? I think I kind of skipped over you because your hand is up. Should I take that as a no? All right. So then I'll come over here and go. There we go. Okay. So that wouldn't work. So we have to start this thing somehow. We're going to start it on a primer system. So we inject some fuel through the primer system into the intake manifold, and we start the engine, and boom, it lights off. Now I tell you, if you don't have a primer system, the old school way of doing it, not a fun way, is you would actually unscrew one of these spark plugs and take a little bit of fuel and pour a little tiny cup of fuel into the cylinder, and then quickly put the spark plug back on, torque it, put it back on, run around, try and start it, and hopefully it started. If not, you repeat that procedure, and then the aircraft would start. So in this particular situation, our aircraft would in fact run. It would go to maximum RPM, and it would run horrible. And the reason why it would run horrible goes back to what we talked about with fuel and the way fuel works. Fuel needs to be in a vapor or in a gaseous state. And what this is going to do is actually going to pull giant globules of fuel, big, I guess, balls of fuel, if you will, into the engine. And whenever you have these giant globules of fuel, you have a smaller surface area, and it has not evaporated. It doesn't work that way. And so you have to have some way to take this fuel, and you have to, I want to say aerate it, but it's actually emulsify it. So we want to emulsify it and make it into very fine droplets. And then when you have fine droplets, what happens is that's more surface area because you have more droplets. So it's the difference between surface area, I guess, if you were thinking about a basketball versus enough tennis balls to equal a basketball, the same size, then you would see that all the surface area of all those tennis balls would be a lot of surface area. And we could take it even smaller, enough marbles, and I would keep going. Anyway, never mind. So anyway, so we have to have some way to actually cause air bubbles to be in here. And one of the ways that we do that is through something called an air bleed. And air bleeds are actually critical to how this whole system works. So the way we would do air bleeds, I'm going to do an air bleed. First of all, an air bleed has to have a source of air that is closer to ambient. So we wouldn't want to put it here, any holes here, because this is a vacuum. So if I drilled a bunch of holes right here to try and get air in here to aerate this, all I'm going to end up doing really is sucking fuel out. So what I could do is I could put a little passage right here and take it up to over here. And of course, it's all got to be higher than the fuel level. Somewhere over here behind the Venturi, and drill a bunch of holes in it. And what would happen, I got to be careful how I draw this, because those holes got to be a little bit higher than the fuel, because the fuel at rest, when the carburetor is not working, is going to come up here and fill this up. So when the carburetor is just sitting here not working, it's going to sit here and fill all up. But as soon as I start the engine and this starts working, starts working, it's going to suck all the fuel back in where it just came from. Suck all the fuel back through here. And now these little air bleeds, these little holes are going to suck air. So air can be what, yellow? So air is going to be sucked through here. Hopefully you can see yellow okay, because I can't. And then it's going to mix air into here. And what that does is it actually makes it, number one, easier for the fuel to come up through here, and it aerates the fuel, emulsifies it, and now we get a nice mixture of fine droplets going up into the engine. So that is our we call it the main air bleed. So let me see what we got. Make sure I'm covering all my stuff here. Yeah, hey, we're looking pretty good here. So let me go back to my notes. Keep. All right. So I added in fuel metering force, and I probably didn't need to. Anybody have any questions or anything you want to go over? I don't see any hands or, hey, is anybody even here? You guys are good. Okay, good. I see people. Hey, Christian. All right, so got out of line here. Let's probably should have did more on Venturi here. So operates on Venturi principle. And we'll just do this. We'll call this one over here for air metering force. Air metering force. So we talked about fuel metering force, now we're talking air metering force. So got it, probably should have did the other way. But anyway, this is the force of air through the Venturi, the force of air through the Venturi. The Venturi. All right. So we have the air metering force and the fuel metering force. Consider the fact that as the engine speeds up, sort of the way the carburetor sees things is that the engine is like a giant air pump. And yes, the engine, of course, is running, it's making the power, but through the carburetor, it's a big air pump, just sucking air through that Venturi. And so the more it sucks air, the greater the air goes to the Venturi, the greater the suction, thus the greater the metering force. In the same way, we have the fuel metering force, and that's the difference of pressure from the float bowl to the Venturi. So if, and I'll get more into this later, but if I could add pressure to the top of the float bowl, in other words, actually like blow into it very hard, it's going to force all the fuel that's in the float bowl down and up and out the Venturi. So if you can add force to the float bowl, you're going to get more fuel. If you add suction to the top of the float bowl, you get less fuel, because it has to be a difference between what is in the Venturi and what is, I'll go back to the picture. It is the difference between what is in the Venturi, the pressure in the Venturi, versus the pressure that's in the float bowl. It doesn't matter if you have a whole bunch of suction in the Venturi. If you have the same suction in the float bowl, you got nothing. So again, it's fuel metering force, which this is why I don't like it. So we said air metering force is technically the force of air through the Venturi. But the fuel metering force is the difference in air between here and here. They should have called it something else, but that's technically what the fuel metering force is. Dominic, your hand is raised again. Do you have a question? Speak now.
Could we get a picture of it? Because inside the carburetor, I said what I typed in the chat. What does the actual meter look like inside the carb? Is it like in the inlet for where the fuel goes in and where the air goes in, or is it like more towards the float bowl?
Say that again.
I said inside the carburetor, you said it has to equal out with the float bowl for the fuel. So do they sit in like different positions, like the actual meter that determine how much air goes? Does that kind of make sense?
No,
Where do the meters actually sit with the Venturi?
Don't quite get it. Maybe, hopefully, maybe you can type me a little something. I don't know. No, sorry, it keeps getting hit. Are those holes grabbing ambient air? Yes. In the in the, bring this back over here, right here in the main air bleed, yes, these holes actually get ambient air, and that's why it's purposely put behind the Venturi. And we're going to look at some other drawings as we go, but instead of my bad drawing. But yes, so it's ambient air. So the fuel metering force has to, I'll say, be greater than the air metering force. I haven't really thought about it that way, but yeah, yes, it does in a way. That's not really how we'd say it. It's just they're two independent things. So, but yeah, and you're thinking about it correctly. So, all right, so air metering force, force of the air through the Venturi. What do I also got? I'm going to make this B for no other reason. This is an important point. Not that something is an important point, but the Venturi, although it's there and its job is to measure the air. That's the only reason why the Venturi is put there. It measures the air and it creates the low pressure that draws the fuel out. So that's really what it does. It does have a negative effect on what's happening. So the Venturi will restrict and limit the amount of air into the engine. Will restrict and limit the amount of air into the engine. So I do think this is one of the Q&A questions, or it's like one of the questions on my test. I will tell you now, it is that what is the actual limiting factor of how much air can be allowed into the engine? And when we limit the air into the engine, we limit the RPM of the engine. And so what is the main limiting factor? It's the Venturi. So if the Venturi is too small, you are going to choke off the amount of air going into the engine, and you're going to have a decrease in RPM. So it is the ultimate limiting factor there. So I've got, let me see. Therefore, Venturi size, that's an E, size is important. It's when you look at, and this is one of the lab projects you have, especially with the Stromberg, guys are given Stromberg, and they were unfortunately kind of cobbled together with a bunch of parts, it appears to be. And so I give you a Stromberg carburetor and you take it apart and you're going to measure, yeah, I was thinking that, Zach, but didn't say it. So when you take the carburetor apart, you're going to measure all these items. You're going to measure the float travel. You're going to measure the Venturi size. You're going to measure the main air bleeds. You're going to measure the fuel jets. You're going to measure all these things. You're going to look at a chart and say, based on these measurements, what engine did it go on? And unfortunately, most of you are going to come up with the conclusion that this doesn't match. But anyway, because they're cobbled together. So I say, what's your best guess? But the Venturi is actually exactly, its size determines on what size engine it went on. So if it is, why not just make them big? Well, if it is too large, it is ineffective at creating suction. It is too large. It is ineffective at creating suction. Sometimes I think of things in much bigger terms, like, well, don't think of it as a little bit larger, think of it as much bigger. So if the Venturi is almost supposed to be about 2 inches, which is actually kind of a big one, what if it's 6 inches? Well, then the air that goes through there has got so much room that it doesn't even act like a Venturi at all. It doesn't even notice it's a Venturi, and you have no suction. It's just some hole that it's going through. But then if it's too small, it restricts the airflow and thus power. So if it is too small, it will restrict airflow. It will restrict airflow. To restrict airflow, and that restricts power. And restrict power. So that's not good. All right. All right. Then the other thing we talked about is, My notes are just all over the place here. We'll come out here. So what about the actual size of it? So about, well, what is the, it depends on the engine, about 1.25 inches, 1.5 inches, 2 inches. Depends on the size of the engine. So if you're talking about like a little A65, we're talking about around 1.25 inches, 1.5 inches. You're talking about a big 0470, you're talking closer to around a little over 2 inches. And is the engineer the one who makes the call to Venturi size? Absolutely. They engineer that in there. And so if you were to take the wrong carburetor and put it on an engine, so let's say we had a carburetor that was set up for maybe an 0320 and we put it on a little 0200, would it work? Yeah, it'd work. It just wouldn't work as well as it's supposed to. In fact, we'll prove that in lab because we have one engine that we're going to use, and I have you guys use the wrong carburetor on it. Of course, you would have never known that. It works just fine, but it runs a little rich. All right, we talked about our main discharge nozzle. Main discharge nozzle. The main discharge nozzle, that is, picture. That is this right here, what I drew going up into the Venturi. That is the main discharge nozzle where the fuel comes out. Now notice it's the main discharge nozzle, indicating that there might be other ones. So main discharge nozzle, that is where fuel is drawn out. Is drawn out into air, entering the engine. All right, and then we also talked about the float chamber. Float chamber. Sadly enough, this has nothing to do with root beer floats, which I really enjoy. I guess that'd be a 1 for some reason, 1. What does it do? Well, it acts as a reservoir. A reservoir for fuel to be used. For fuel to be used. 2. It controls the level of fuel, at the discharge nozzle, at the discharge nozzle. Oh, I can say without it. And it controls the level of fuel discharge nozzle. I could put with the help of the float, because you really got to have the float in there too. You can't just have this chamber, it doesn't do anything. Without it, fuel would just run out of the nozzle. Fuel would just run out of the nozzle. And so going back to here, okay, going back to here, this, I said this dimension right here is critical. And in fact, it's so critical that you have to actually, it's one of the main things that you measure when you're overhauling carburetors and putting it back together and you're resetting it, this critical dimension. Well, this dimension is actually set over here because it's the same thing. And so like Stromberg's, the older style carburetors, you actually put a micrometer, it's called a depth micrometer, and you put it across the parting surface right here. So from this point to this point, and it's the depth micrometer, I'll show you guys when we're in lab, actually goes down until the little the anvil thing comes down and it touches the fuel level. And so this is a critical distance here, which means that it's the same thing here, but you just can't measure it in there. So what you have then is this, because this dimension right here has got to be set, and the way you actually adjust it with the Strombergs is you adjust down here the seat where this goes into. You can put shims and stuff, and we'll talk about that in lab. In the Marvel Shebler, the other type, you actually end up just bending some stuff up here, which sounds horrible, but that's kind of the way it is. Because If this dimension, if the float level is allowed to be a little bit too high, then you're out of calibration. So they figured out, okay, so you have X number of pounds of air are going through here. It's actually not pounds, it'd be more volume because this doesn't measure pounds. So if you have an X number of volume going through your Venturi, it's going to create a certain amount of suction, and that suction is calibrated then to take a certain amount of fuel out. Well, if the fuel level is too high, that means it takes less suction. So it's going to be easier for the fuel to go out. And if it's easier for the fuel to go out, then that means that it's getting too much fuel. So if you, and same thing, if the fuel level is way down here, it takes a tremendous amount of suction to get that fuel to come out of the discharge nozzle. And if it takes a tremendous amount of suction, then that means, for example, at any given RPM, the engine's not getting enough fuel. So it's going to run lean, not enough fuel. Or if the fuel level's too high, it's going to run rich. It means it gets too much fuel. So let's see. I was looking at some questions here. Mark says, what is going to cause that to wear out? What part, Mark? What's going to wear out? Not a lot of this. I'll tell you what wears out. It's nothing on here so far. It's the throttle bushings wear out. We'll get into that. Throttle bushings create a big problem. This stuff doesn't usually wear out, but when you do change the float, or we do change needles on a lot of these when we overhaul them, I guess, because the needle kind of gets a little wear out into it. You have to reset all this. It's easy to do on the Strombergs, or sorry, the Marvel Shovelers. The Strombergs are really kind of a pain in the butt. Carb monkey. No, I don't want carb monkey. Go away, carb monkey. All right. Let's see. Uh-oh, the internet connection is unstable. If you guys have any glitches going on, message me, let me know that we have glitching. I can tell by the amount of noise going on outside of my office that I think Fortnite has just begun out in the other room. So let's see, main discharge nozzle, float chamber acts as a reservoir. We got that, controls. We'll make this point three. Fuel enters the float chamber from a fuel supply. Fuel enters the float chamber. Float chamber from the fuel supply. From the fuel supply. All right, so normally I would say, hey, what is our fuel supply? But since you guys are all muted, our fuel supply is the fuel tanks. And the fuel tanks are going to pretty much be in one of two positions. Either they're going to be way above the carburetor in a high wing aircraft, or it's going to be about the same height as the carburetor, which is a low wing aircraft. So in a high wing aircraft with a float carburetor, you do not have a fuel pump. It's just gravity fed. So like my little Cessna 150, Cessna 172s, 182s. I wouldn't say 210 because that's a different stuff, but that has a fuel injection. So anything with a float carburetor with a high wing does not have a fuel pump. But anything with a low wing, period, any low wing aircraft, you can count on it having two fuel pumps. One in the fuel tank and one on the engine. And one works as a backup to the other. So, all right, fuel supply. So gravity feed systems, gravity, which means no fuel pump, high wing aircraft, feed system is about 3 to 5 PSI. I think that's actually sounds a little high to me, but the term for this is also called head pressure. Head pressure. So if we said we need more head pressure on something, it means you raise the tank up. Let's see, B. So pressure systems, or I'll put low wing. So systems with fuel pumps is about 5 to 20 PSI. All right, we have fuel metering force. We talked about fuel metering force. That brings me to air bleed. Oh boy, did I mess up here in my notes because I got out of line. So we'll make this one, main air bleed. Main air bleed. We talked about the main air bleed. Let's make sure you go back here so everybody remembers what the main air bleed is. Say by a carb monkey. Like all right, so the main air bleed was this item over here. Is this item over here where it has holes drilled into it in an ambient air position that allows ambient air to get sucked in through here and up and emulsified into here. Now, if you guys did the reading, one of the things that, let me see. Yeah. One of the things that you would have seen is their demonstration. I'm pretty sure it's in your book. Demonstrate, let me see, pen. What do we got? Where they demonstrate with a cup of water and there's a straw in this water and a person sucking on the straw. And let me see. We have our liquid in here. And when you suck on the straw, it takes a certain amount of pressure to draw this liquid up. And they demonstrate that, well, if I put a hole right here, it doesn't change anything. It doesn't make any difference. But if I put a little hole right here, somewhere above this, when you actually draw the air in, well, if you ever had a hole in your straw, it really sucks because you don't get the kind of fluid that you wanted. You end up getting this aerated, half water, half air kind of a thing. The air bleed is on page 212. There you go. And I think maybe I do have a picture of it. Let me see. Oops. What do we got here? Because they can draw better than I can. Let me take a look. Did I put the section? No, I did not. Well, there you go. It's in your book. All right. Back to, okay, so main air bleed. What do we say about main air bleed? One, helps break up the surface tension. Helps break up the surface tension. Surface tension of liquid fuel. And let's see, everybody's had 300. No, you guys haven't all had 300 yet. So all my 300 people, you know a lot about surface tension. We go into a great deal about surface tension when we talk about non-destructive testing. But for those of you that haven't had surface tension is what we see when, like if we put a straw in here, we would actually notice that the level in the straw would be a little bit higher. Stop that. And we'd actually notice that it actually goes up on the side of any sort of cup. That's called meniscus. I wish, all right, so my tech guys, how can I make this not do that? Because I hate that it keeps doing that. So that's on you, Hector. So surface tension means that then if we had the main discharge nozzle, the fuel wants to actually stick a cohesion to the side and don't, well, yeah, I know that. Do what, Hector? If I hold the pen right here, it does this. And so if I'm drawing like really slow, I keep getting the menu, and I hate that. Okay, so anyway, so you want to break up that surface tension. Otherwise, the main discharge nozzle, the fuel would come up and it would just kind of want to sit right there, and it wouldn't want to go out of the discharge nozzle or the straw. So having the holes all the way through, break up the surface tension, allow the air to come in, and makes everything work. All right, helps break up surface tension of the liquid fuel. What else do I got here? 2, helps lift fuel to discharge point, helps lift fuel to discharge. point. It takes less suction to actually pull the fuel out. And 3, helps provide a more uniform, a uniform mixture of fuel and air, more uniform mixture of fuel and air. And last point, and I'd said this one, creates more surface area, more surface area of fuel for faster evaporation, more surface area of fuel for faster evaporation, EV, faster evaporation. All right, let's see, do all carb types have main air bleed? Absolutely. And August, it's 420. All right, you would notice right now. Okay, so I'm gonna stop here and I'm gonna see you guys in a couple of minutes.